Hello, and welcome to another LXD release livestream. I'm Stefan Greber, project leader for LXD, and this is going to be LXD 5.12, which has been released on Thursday, with the actual release announcement coming in a bit later than usual on Sunday, mostly because I was busy with other things on Friday. As far as new features, it is a pretty light release. You're going to see there's just 3 new features in there, but there's been a lot of work that has happened. You can actually see that easily enough. You go down in the announcement and you expand the full list of commits. You're going to see that a lot of stuff has happened. Just relatively few of those are new features. That's because we're doing a lot of reshuffling in our storage and migration logic, cleaning things up a fair bit ahead of work that should land maybe in the next release, around specifically live migration and improving the way we do both container and virtual machine live migration to make things more flexible and a lot faster. So that's why you're not seeing a ton of new features here. We've been busy with other things. Now, on the new feature front for LXD 5.12. So there's 3 things that are worth mentioning here. We've got support for something that's been requested on and off. We never felt like it was a super good idea, but now that we need it ourselves, we finally implemented it, which is support for LXD to effectively force the creation of a storage pool. So if you're trying to create a storage pool on a device that has an existing partition table or an existing partition on it, LXD right now would just fail. And that's because it doesn't, like the different tools we use to create file systems, we don't really want them to like potentially corrupt data. It's usually an indication that you do have data there, so we don't want to go and just like stamp over that and just destroy it. But there are a number of cases where it's safe, like this machine has been just like freshly reinstalled. If there's anything left on there, it's like a leftover from a previous life, you don't care. So now we've got a new config key called source.wipe that you can set to true at the time of creating a storage pool, and that will instruct LXD to go and effectively blow away the first 4 megs of the disk, removing any header as part of that, and then the file system creation will usually succeed. The next thing we've implemented, that one is effectively going to be invisible for pretty much everyone. It's support for generation IDs. So that's a pretty new concept. I think we only heard about it at a kernel development conference back in September. The general idea is that Linux and a bunch of other operating systems do a bunch of crypto initialization on boot, things like initial seeding of the random number generator and things like that. Now, this is usually not an issue because you can't really have 2 VMs having the exact same state, so it's perfectly fine and safe. The problem with that is with virtual machines, it's actually possible to do a stateful snapshot and then restore that state. And if you restore that state, now you end up with effectively 2 versions of that VM, the old one that was running and now the restored one that you just have now, that have the exact same state, including the exact same random number generator state at the time. That's a bit of a problem. A lot of operating systems would like to know when something like that happens so that they can go and reset those things like random number generator, but also some amount of crypto libraries in user space. And generation ID allows you to do exactly that effectively. So what that looks like is the LXD virtual machine still has a UUID, which is an identifier for the VM itself. That UUID will not change during a snapshot restore. It will only change if you copy the VM, like the new VM created from a copy won't share the UUID with its parent. But when you restore a snapshot on an existing VM, its instance UUID itself will not change. However, the new thing we introduced now, which is the generation ID, that one will change. And that means that the VM guest itself can, at boot time, cache what instance generation ID it's getting. And then if that ever changes at runtime, that indicates that the VM state was effectively restored, or the VM went backwards in time or something like that. And it will know to go and reseed those number generators, also clear potentially some cached keys, some cached random data to get back into a clean state. So it's a security feature that should be effectively invisible to just about everyone, but that will make things slightly safer. And the last feature in this release is support for a new config key called io.cache, which lets you control the block cache mode on virtual machines. There are effectively three options there. The default value is none, and that means that LXD will just use direct IO with no caching whatsoever on the VM. That's usually the best option really on any kind of fast storage in VME or anything like that, because you just, instead of potentially duplicating memory, caches, and all that kind of stuff, none of that happens. The cache comes straight from the underlying storage or operating system. And all of the writes that are sent are effectively guaranteed to be sent all the way through to the block device, and everything is consistent. Now, the second option there would be to use writeback, which instructs the virtual machine to, the virtual machine hypervisor, effectively runtime, to turn on some amount of caching. So writes will be cached only when the guest requests that something is flushed. Will the data actually be guaranteed to be committed to disk? That means that if you lose power, it's possible that some data will be lost, and something that hasn't been explicitly flushed from the guest might be missing. And then we've got the third option, which is called unsafe, and that one is obviously, as the name implies, far worse than the other two. What happens with unsafe is that flush requests from the guest are also ignored. So the guest will think that it's doing a consistent write, and it's not. This is fine in some environments. The reason why we wanted that config key specifically for ourselves was for testing environment, like CI environments, where we've got scratch drives that are there just to store data used by tests, but those drives are completely reset on boot. So we absolutely don't care about any kind of consistent storage on those. And the hypervisor should feel free to cache as much as it wants to provide as good a throughput as possible, because we absolutely don't care about data consistency or about potentially losing data if the machine loses power or something like that. So now that's not, all of that is now available as through a config key, so that should be a pretty useful tool for a bunch of people. All right, so with that done, now let's just go through that again with a demo. And as usual, I'm using my demo project here, which is empty. And the first thing we want to do is actually create a storage pool. So let's create a storage pool, call it demo. And the source is devloop69. That's the block device I've got set up. It's like a 20 gigs loop file I just set up earlier. If I do that, I actually need to specify the backend when I do ZFS in this case. And this fails. It actually says can't do it, contains a file system of type ext4. Now, normally you would then have to go and manually go and clear that. That's not a huge deal on a single user system. The reason why we wanted the config key was because we're working with clusters a fair bit, and it's pretty impractical to go and SSH to 20 different systems and go and clear partition table on all of them. So now you can just do source.wipe true. And there you go. The header has just been flushed, and then the file system creation succeeded. So that's really all there is to that. I'm just gonna delete that storage pool because I don't actually need it. And here we go. Now, the next thing to show is the generation ID. So for that, I'm just gonna be launching a new VM. So 2204 cloud v1 as a VM. And there we go. So if we look at the QEMU output here for that, you can see the arguments being passed, and there's something new here, which is device VM gen ID. And we can see it right here. That's a UUID that has been passed as part of this. Now, if you look, you're gonna see that the VM UUID, which is right here, happens to be identical. And that's normal for the initial boot, and normal until the VM has been restored from a snapshot. So let's just stop the VM to make sure that everything is consistent, and gonna do v1, create a new snapshot code foo. And if at this point I would start the VM, I would expect it to still be using the same UUID, and it is. So just let it boot, then we'll shut it down, and then restore it, restore that snapshot. And when we do that, the instance UUID won't change, but the generation ID will. So let's just stop it. There we go. And now do restore v1 and snapshot goes code foo. There we go. And we start it again. And look at the output. And this time we can see that the VM UUID itself has not been modified. That's still the same we had before. But the generation ID, which is right here. Oops, right here. Actually, I looked at the wrong one. This is the instance UUID right there. And this is the instance generation ID, which we can see has been changed. So that's effectively all there is to it. Now the kernel in the guest operating system could detect that and take action, whatever that means. In this case, I didn't do it with stateful snapshots, so it doesn't actually matter all that much to the guest, because in either case, it went through a full boot, so any crypto state that might have been present will have been flushed. It's very unlikely that a guest would actually store crypto state on disk to be restored on boot, so it's very unlikely to matter in this case, but matters a lot more if you restore a stateful snapshot instead. All right. And well, actually I could have just used the exact same VM to show you the last feature. So it just started back up for that. And oh no, actually I can't easily do it with that because my storage is just too fast. So let's just delete the VM. Oops. Okay. And then we launch the VM again, and this time I'm gonna be doing storage, I think it's called remote, which is a Ceph cluster. And this is going to be particularly slow because my desktop here is connected on Wi-Fi. Pretty decent Wi-Fi, but Wi-Fi nonetheless. And that Ceph cluster is on my servers in my basement. So the Ceph cluster itself is pretty fast, but the client that I have here is not. It's going to be capped at like 300 megabit per second, pretty much. So the best I would expect as far as writing stuff to disk within that VM is going to be around 20, maybe 25 megabyte per second if I'm really lucky, but could also go lower than that because with Ceph you need to actually do your writes 3 times for application. So it could go all the way down to like 10 megabyte per second or something like that. So let's go in there. And what I'll do is I'm going to write 400 megs of zeros to a file called foo.img in chunks of 4 megs. And also indicate that at the end of the write, I want to flush everything to make sure it's consistent. So that we don't just measure how fast memory is, but we actually measure how fast storage is. And I believe DD already kind of does the timing stuff. Oops, this is off, not out. There we go. Okay, so that will get us throughput, and from DD itself also measured system time to just make sure everything works as expected. And as you can see, this is pretty slow. All right, so we wrote 400 megs, 32 megabytes per second, which is actually pretty darn fast considering, and that took 13 seconds. Okay, so we can just remove foo and shut down the VM. Okay. And I'm going to go ahead and config device set on the VM, which is v1, root disk, and I want io.cache to be unsafe. There we go. And start the VM backup. And so I'm using Ceph in this case. Ceph has separate configuration for its caching behavior. And in this case, it's using ceph.conf. And here we can see I've got the cache size, which is 2 gigs in this case. I specifically say I want the cache to be enabled immediately. I don't want to wait until Ceph will have noticed the guest doing a flush, so I just want the cache immediately set up. The maximum amount of data I want the cache to hold at any one time is 1.8 gig effectively, and it should try and empty as soon as it reaches 1.5 gig. That can be tweaked a fair bit. This is quite high, but I've got a lot of memory on the system, so that works out. On systems with less amount of memory, you probably want to go ahead and use smaller values. Anyway, we're back in the guest. I'm going to do the exact same thing. And this is seemingly slower than I expected. So what is going on? Yeah, it is faster, but it's not as fast as it should be. This is interesting. So I wonder if maybe the VM was writing a bunch of stuff at boot time and the cache is still full. Oh yeah, there we go. Okay, that's what I was expecting. So I think what was going on with the first one is we did get a bit of a boost, but the cache was still mostly full just from the VM booting. There was still a bunch of data in there that was still to be flushed over the network in the background. Whereas the second time, the cache was effectively empty, so we got to get the full 1.7 to 2 gigabytes-ish write speed on it. And that's still with the guest requesting writes to be consistent. So as we can see, we are in an actual unsafe mode because the guest is asking us to be consistent and the actual backend doesn't care. So that's perfect for testing, not something you want to run in production. But yeah, for any kind of CI environment or testing environment or development environment, this really, really helps. All right, I'm just gonna shut that one down. And that is it. That's really what we have for LXD 512. Now, one thing to keep in mind, usually I finish those videos by saying that this is rolling out to users over the next 48 hours or so. It is going to be slower this time. The reason is not because LXD 512 is particularly risky as a release, it definitely isn't, but because we are using the opportunity to also switch from Ubuntu 20.04 to Ubuntu 22.04 as the base for the snap. And that part is a bit more risky. We found a few bugs, we fixed a few bugs already. There's still one issue I need to sort out before I feel confident with rolling that out to any user right now. If you want this immediately and you're going to be refreshing to latest candidate, be aware that until we start rolling it out to stable, there is a bug that effectively causes a bunch of mount issues that can do anything from failing instance restart to failing deletion. So if you do move to latest candidate right now, please reboot. A system that's been rebooted after the switch to the new channel won't have the issue anymore. But if you need to keep the system long running, don't use candidate right now. Over the next day or so, we should have that issue resolved, and then we'll start rolling it out to stable, and we'll keep a pretty close eye on what's going on the forum for any early feedback of anything else that we missed that got broken. We've had the Edge snap move to 22.04 for a couple of weeks now, or something like that. So all of our daily tests and all that stuff we know work just fine. We've validated it on all of the distros we test on usually. So it should be pretty solid. We don't expect it to blow up for everyone, but there's potentially, there's a lot going on in the snap, and it's perfectly possible that we missed a few corner cases here and there. That's why we're going to be rolling it out much slower than usual, so we can react to anything that we didn't notice so far. And that's it for LXD 512. So hope you enjoy those new features, and I'll see you in the next video. Thanks for watching. Bye.